sequence of 1.4 nano or 14 angstrom using 7 nanometer technology. Oh, really? How do you do that? I mean, well, logic folding. So I'm going to tell you all about how logic folding will give you an opportunity to beat advanced 2D with legacy 3D ICs. Okay? Now, I've been doing this research for quite some time, and every time I present 3D ICs, I get two questions all the time. The first is, where's killer app? What 3D IC can do for us, during my everyday, life, right? And the second question, of course, is thermal. Chips get hot, right? So how do you cool down? Now, as far as killer app, there have been in the past, there are some commercial products that use 3D IC. For example, image sensor from Sony, right, has been using 3D IC for quite some time, where you have the image, photodiodes and all that, right, sitting on the top, and then below it is your memory, and then also below it is your signal processing. And also you heard about AMD's V-cache, where you stack last level cache on top of CPU to give you a better experience in gaming, right? And then you also heard about Intel's Foveros 3D IC, right, that improves the yield of 10 nanometer technology by stacking 22 and 10, right? So, but these are some of the small scale applications of 3D ICs. But these days, we all heard about how South Korea was so happy these days with this thing, HBM4, right, or HBM. That is a perfect example of, killer app for 3D IC. Basically, HBM stacks DRAMs, right? 12 of those. And then the base die is logic. And then every time you use AI services, right? So the data that's stored in HBM is what you guys are using, right, to get your tokens back. So 3D IC finally has a killer app that everyone is using, and that's HBM. But then it's only when you use your 3D ICs with your hand on your cell phone. Okay, then that's when we know the 3D IC is indeed invading our daily life and proliferate. Right? Now, I heard an announcement from Huawei this fall. They will use Kirin 2026, right? And then use 3D IC technology. So, this is exciting. So they said they're going to deliver 1.4 nanometer technology with 7. The way they achieve it is logic folding. So we need to know what logic folding is, right? So to look at it from a very easy perspective of here, logic folding is like folding a paper, like you see over here. So if you fold the paper of that ratio, right, 2:1 into half, a lot of things are improving, but especially length of wires, right? So for example, this AB line, if you literally fold up, right, length becomes 0. And then corner to corner distance, A to C, after you fold this up, just becomes that. So folding gives you one very promising, fact, that is connection length will reduce. That's pretty important in IC design because delay of a circuit, right, is a lot dependent upon how much you time on traveling between devices. Basically, delay caused by wires, right? But then if the length of the wires are getting shorter, right, the delay is going to improve, right? That's exactly what Tau law is, expecting. Instead of doing more research on how to tackle long wires, Tau law, right, is basically reducing wire delay by folding your design. Now, I did compare 3 different design granularity of ICs over here, especially 3D IC. So 3D IC can be designed at 3 different levels of granularity. So I call them coarse level or die level 3D IC over here, right? Or what you do, right, is you just stack 2D ICs on top of each other to create multi-tier 3D IC. So that we already see an example of it, right? So HBM is exactly a good example of that. But then you can do a more fine-grained 3D IC design, where each die will have some functional modules in it, right? So what you then would do, right, is you break the hierarchy of all these dies into modules, and then you can move these modules between different tiers and optimize your design. So we call that block level design. You can do even more. You can synthesize all these blocks that have large gates in it. Then you can move individual gates between the tiers. Okay, so that's the granularity difference. And in LogicFolding, with the Huawei's approach, right, is tackling the last two. So they can either move around blocks in between tiers or gates. Again, big benefit is if you fold your big design in one plane into multiple tiers, the connection length is going to reduce. Now, each granularity gives you different pros and cons. Not everything is perfect, If you want to just stack existing 2D designs, design is going to be easy because you already have 2D designs. You just have to stack them. Of course, you need to add stairways or elevators to go from one tier to another, so-called the TSV islands that are located in the middle, right? But then the design is not going to be too hard. So, and the number of connections between the tiers, right? So currently, HBM has only a few hundred connections for signal, and then a few hundred more for power delivery. Number of connections between the tiers is not many. So with that, you can just manufacture it quite easily and then have a high yield. But then performance-wise, if you just everything at the course level, your PPA is not going to be very, very competitive. Versus if you do your design right at the block level and a gate level, right, you need to move around a lot of things. You need to optimize a lot of things. You have to basically look at individual gates, right? So your design effort is going to be seriously more complex. But the number of connections between the tiers will also increase quite a bit because every gate, will need connections if you have your neighbors in other tier, right? So this fine-grained 3D IC has EDA and yield challenge. But then since you're optimizing your design in a much greater depth, right, your performance is going to be much better. So later on, I'm going to show you a comparison between these granularities. Now, here is a real example of folding a processor. Okay, we're not folding papers, but we're folding processor design layouts, right? So I'm going to show you two options of folding a processor. First is weak folding, and second is strong folding. So this is my starting point. So this is OpenSpark T2 implemented with 28 nanometer technology. So it's got 8 cores, 8 L2 data cache, and other modules. So we did this implementation. By the way, this was supported by Intel. We did this study 12 years ago. 12 years ago. So back then, some companies were already interested in folding. Just that they never commercialized the chip, like how Huawei is working on. They just did some study, right? And I was part of it. So one way you fold this is you add this cut line over here, and then literally just fold it, right? But then when you do that, your design will improve a little bit, but then, not as much. Folding reduces some wires, but what you want to do, after you fold, you want to move things around. So you get more saving, right? So it turned out what I did, right, is I moved around all these, cores in the top tier, and then I moved all these, cache blocks on the bottom tier, and then rearrange these, functional modules in the middle in this way. So we call this level 1 folding, level 1 folding, okay? But when you do that, your area reduces from here to there, and then connection with wires will shorten, right? So you get PPA improvement, performance, power, right? Wire length. So I will show you the numbers later on, but then right now I'm just giving you a high level perspective here of what's happening with folding. Right? But then I didn't stop there. I kept on folding recursively. So for example, this one, right? I took this core and then folded. So this is top portion of this guy folded, and right below it is the bottom portion of this guy folded. In fact, you can keep on folding until you cannot anymore. And then the more folding you do, the better your PPA will become. Again, later on, I'm going to show you all the results with simulation and all that. Now, so Huawei is working very hard on making this possible. And of course, nothing in life is easy. There's always challenge, right? So according to Huawei, there are two main challenges that must be overcome to make this happen. First is, okay, the first is existing chip design software. That's exactly what Tingbo mentioned herself. The biggest challenge is design tool. We all know how digital chip design is not done by human, but it was done by computers and algorithms, right? EDA tools. So basically, we need better algorithms to design logic folding chips. All these folded designs that you see here, I didn't do it manually. It was done by computer algorithms. I'm going to tell you later on how those algorithms work. So we don't do this design ourselves. We let computer do it by designing and executing algorithms. Some algorithms are AI-based. Some algorithms are based on traditional methods. So I'll tell you all about those. The second issue, of course, is heat dissipation. So the more chips you stack, the higher the temperature of hotspot becomes, right? So cooling continues to be a challenge in 3D IC. So with that, I brought 3 parts today for my talk. The first is I'm going to show you again more details of folding that I did with Intel 14 years ago. And then I also repeated this folding study with Samsung a few years back. So I'm going to show you those results first. That's my first part. And second is, as I said, again, all these folding designs, computer generate automatically. So we need to design algorithms to do that automation ourselves. So I'm going to tell you a bit about those design tools that do design automation. Okay? And some of them are based on traditional approaches, and some of them are based on AI. The third part, actually, I had a chance to do a test chip. I brought some chip samples. So I'm going to pass it around, and I'm going to tell you about this chip here. This is the real 3D IC chip that I did 12 years ago. I'm so happy that all the things that I've done like long time ago finally, is reviving. I'm so happy to see this, thanks to Huawei. So, a bit more details about folding and its impact on PPA, right? Power performance area. Intel first, and then Samsung next. I definitely, I'm working with Huawei to do this and update our numbers. Now, I don't enjoy bragging on myself, but then this one I definitely have to brag it because I believe that this is the first paper that demonstrate folding, okay, but also provided EDA algorithms that enable it. So this paper we wrote about 12 years ago, published at DAG, arguably is the first paper that talks about folding and PPA and EDA algorithms all together in a single package. So we saw this design before, right? Actually, I have done level 3 folding. folded once, I folded twice, and then I folded 3 times. I did 3 levels of folding, right? So this is my first level of folding. So after cutting, I'm going to move these guys here, and I'm going to move these guys here. That's my level 1 folding. Level 2, right, is I take this guy and then cut it like that. I'm going to move these guys over here, and then I'm going to move these guys over there. That's level 2. But I did not stop there. I did level 3 cuts, where in the top half, I cut more, and then I moved some of them here on the bottom, and then I moved some of these guys to the bottom. So I kept on cutting and cutting recursively. Every time I cut, my PPA improves. The quality of the folded blocks get better. Why? Because you look at this example, that is a core, right? If you look into that core, you see this. So in that core, you have LSU unit, FGU unit, execution 01, table lookup, et cetera, right? So all these blocks sitting in this core can be partitioned into 2 tiers. So for example, LSU, this guy, you go to top, right? FGU, you go to top, right? And execution unit and 1 and 0, you go to the bottom. So again, you can fold and rearrange these modules inside. If you do this level 2 folding, you get this much of improvement. First, 13.3% shorter wire length. You see, connection between LSU, right, and an IFU were this long, but now they're sitting on top of each other. Vertical direct, distance is much shorter. You see? So all these connections between the blocks are getting a lot shorter. That's what I said as a benefit of folding. If you fold it, wires are getting shorter. And we see the exact example of that here with the real chip design. So 13% improvement on wire length. And if your wires are shorter, fewer buffers are needed. What do I mean by that? If you want to run at chip, certain chip at certain speed, you need to, make sure that your chip runs at that target speed, right? To do that, you need to add a lot of timing buffers to speed up your delay. So then buffers that you have added, right? It all depends on how long the wire. If your wires are shorter, you need fewer buffers. Make sure your chip runs at that speed, right? And then also you can make your transistors big or small, right? So if you make your transistor bigger, their speed improves, right? So we call this, transistor sizing. To meet your timing goal, people have to, enlarge your transistor a lot, but you don't have to do too much if your wires are short because your delays are small. All of those contribute to power saving of 14%. What that means, right? Power consumption of this versus power consumption of both of these guys, these two is 14% better than this guy. Folding. Right? Now, this folding, can we do this manually? No. You need to use computer algorithms to do this automatically. What that means, if I give this to my algorithm, the algorithm will generate these two automatically. I'm not doing anything with my mouse. It's the computer algorithm that generates these two from this automatically. How is that done? I have a lot of slides to tell you how I automated this design, automation. Now, level 3, And like I said, I did not stop folding. I kept on folding, right? So that's what you just saw from previous slide. Now what I did, right, is again, I chose execution unit 1, which looked like that. And then I folded into this and that. Folded. And then I put the top piece in the top tier and then bottom piece of it right below it. You see, you keep on folding, keep on folding. So I did that, right? With not only this block, but these other blocks I also folded. So LSU, became LSU, where is it, top, and then LSU bottom, right? So this guy became this and this, you see? So you can keep on folding. That's what Hawaii is doing. That's what Hawaii is doing. When, Ms. Tingbo said she's using logic folding to beat 1.4 nanometer with 7, that's what they're doing. Folding and folding, folding. Why? Folding gives you improvement on performance. How is scaling? Delay is improving. It's not EUV. It is this folding and stacking that makes this possible. So, double 3 altogether after folding these 5 guys gave us 9.2% wire length saving and 10% power. If you're buffer savings altogether, they gave me 5% power reduction. Keep on improving. One thing I do want to talk about is why these 5? Why not this? Or why not that? Or why not this? Because some blocks, even when you fold, doesn't give you too much saving. Some blocks, if you fold, you get a lot of saving. So how do I know which block to fold or not? Right? It's a very important research question. So instead of solving it with machine learning and trained data, and back then, 12 years ago, we didn't have machine learning or ML-based approach available. So we did something very easy, right? So we looked at individual blocks here and then said, okay, ask ourselves, okay, do these blocks consume a lot of power? If they consume a lot of power, then we expect more power saving. But if these blocks don't consume too much power, we don't expect too much power saving, right? So we looked at the power consumption of individual blocks and see if we want to fold it or not. And then another thing I did, right, was ask ourselves if these blocks have lots of wires in it. For example, does this have a lot of wires in it? Or does this have a lot of wires in it? Why do I care about the number of wires? Because folding shortens wires. So if your block do not have too many wires, folding will not give you too much saving, right? In other words, if your block has lots of wires, folding will give you lots of saving on wire length, right? So in the end, what I want are the blocks that consume a lot of power and that have a lot of wires, you see? This was the criteria of deciding which block to fold. If you're doing PhD and want some research topic, maybe you can look at other factors, right? Instead of just looking at power consumption and number of wires, you can look at other features and use them to better predict the saving after folding. Another research problem, right, is now we're focusing on power consumption, power saving, right? But then, in fact, Huawei is interested in improving performance. So which block we want to fold so that the overall longest path delay is reducing? Open research question, okay? Now, if you fold, we need a lot of stairways, a lot of elevators to go from one tier to another. So this is level 1 folding, basically this. The other one is level 3 folding. And I'm showing you how many elevators or dotted eye connections are needed. So if you do a very weak folding, you only needed 7,000 stairways or elevators. But if you do lots and lots of foldings, you're going to need 100,000 elevators. Now, your foundry will need to manufacture these guys. Which one do you think is harder to manufacture? Which one between these two harder to manufacture? Now, you see the one on the right. The more shapes you have to fabricate, the harder it becomes, right? So this one obviously is going to give you some challenge and yield. But then if you pay that price, performance is going to be much better. This is the overall comparison of 2D IC, weak folding, level 1, and level 3 folding in terms of performance, power, temperature, et cetera. That's the ultimate comparison here, right? So first of all, this is 2D IC, the commercial 2D IC. That is, to remind you one more time, this. The middle column that you saw from the table is this. And then the last column on the right is this. I'm going to evaluate the quality of these layouts in terms of power performance, area, and temperature. So, first of all, performance. You'll notice that their performance is identical. So what's happening here, right, is I'm going to run all 3 chips at the same speed. Then I'm going to compare power. This is so-called ISO performance power comparison. Run all the chips at the same speed, then see who consumes the least amount of power. So your battery lasts longer, right? So turned out your level 3 folding design has about 20% lower power consumption than your 2D IC. Why? Like I told you, if you keep on folding, right, your while until it gets shortened, number of buffers you added is smaller, right? So all of this combined here, and the entire chip has 20% better power saving. Your battery will last 20% longer. To get this, we didn't use EUV. We didn't use advanced node. All that we did was to fold and bond the dies to form 3D IC. That's exactly what Huawei is doing. Logic folding, improve the quality of your chip. Now, size of the chip also is half because you're folding one big paper into half, so size also reduces. So for the application where chip size is important, for example, smart glass, your chip must be small and less power, right? You don't want to charge up your smart glasses every hour or every 30 minutes. So size-wise, also this is another edge. Although your temperature goes up. Instead of having one chip, if you stack 2 chips that generate heat, the heat coupling will make the whole chip temperature going up. So the overall impact is one plane, one die 2D, right, is 45 Celsius, but in 3D ICs, level 1 folding is 61, level 3 is 57. You may think that the more you fold, the harder the chip will become, right? But turned out that's not the case. And this was quite surprising to us. So some people may say, hey, if you fold, doesn't your temperature go even worse and worse and worse? Right? The answer is no, actually. Why is that? Now, if you fold your functional modules, power density goes up. For the same area, you have more transistors that generate heat or consume power, so power density goes up. So it used to be that this core has that much power, power density, but after you fold it, the power density goes up because for the small area, you have the same number of transistors. That means, density of power consumption per unit area goes up, right? So this is why people may be concerned that folding will make temperature worse. But turned out, there's another part of the story here. If you fold your chip, you will use a lot more die-to-die connections. The way you bond the chips together in 3D IC, you use copper pads, okay, to stick them together. High temperature, high pressure bonding, right? And then these copper pads that you see in yellow color actually dissipate heat. It allows heat to go through and go to the heat sink. If you don't have these metals, your heat has no way to escape from the core. So the heat just remains there. But then if you have these vertical metals, it dissipates heat vertically. In other words, thermal conductivity improves with more metals connecting the two dies. The thermal conductivity, right, is much better than level 1. So combine these together, power density gets worse, thermal conductivity gets better, temperature is power times 1 over thermal conductivity or thermal resistance. Putting it all together, your temperature is better with more folding. So we have this good news to Huawei. Huawei, keep on folding because your PPA, performance power, will get better. And the temperature, better. Oh, I want to do it now. You need more advanced design tools. Okay? Now, this is what I did with Samsung. So Samsung, they saw what we did with Intel. So they wanted to do some upgrade. Because back in 2014, that was a long time ago, they wanted more modern processor, and they also wanted more modern technology node. So instead of using T2, they wanted us to use ARM processor that they are currently using. This turned out to be A53, not a very big design, but still meaningful commercial core. And then my technology node is not 28, but 16. And then they wanted us to repeat the study and see how much, folding 3D IC, fine grain 3D IC improves 2D IC. Okay? So for that, we have done 3 designs again, right? So the first design is, 2D. This is A53 implemented in 16 nanometer quad-core version. And then, this, we showed it to ARM, and ARM was happy with that design. We did not make 2D bad on purpose. No. We wanted a very fair comparison, so our 2D design is competitive. Now, the first 3D IC design is where I put all the last level cache in the bottom tier and everything else in the top tier. And this is so-called memory on logic stacking. But then the way I glue these dies together, I use solder balls. Instead of calling it solder balls, we call it microbumps. Microbumps are small balls, and then there's spacing between centers. We call it pitch, and that number is very important. So we use 10 micron pitch microbumps to glue these die together. Now the third 3D design, we bonded the 2 dies, without using balls, but we directly bonded copper pads that sits on top of the top metal layer, M-top. So we call that hybrid bonding. Hybrid bonding. The hybrid bonding gives you actually a smaller pitch, so you can add a lot of connections between the dies. Okay? So we use hybrid bonding with 1 micron pitch. You'll notice that this routing, right, it looks different between these two, although partitioning is the same. Because different bonding will require different design. The fact that you're bonding with microbond with 10 micron pitch versus hybrid bonding with 1 micron pitch, your circuit design needs to optimize this bonding differently. That's why these two designs are different. We're not just using the same design. We optimized our design based on bonding. Now, we played this trick, and this really works. This really works. This is so-called metal layer sharing. So what do you mean metal layer sharing? If you look at this net 1 that connects the transistor on the top and the transistor on the bottom, you need hybrid bond pad because you need to connect dies in transistor to 2 different dies. So you need that elevator to go from one tier to another. But then if you look at N2, N2 connects transistors in the same bottom die. This connection, you don't need this elevator to go up. You can stay in the bottom tier, right? But then what N3 is doing is slightly different. So N3 is connecting 2 transistors in the top tier. But then the routing, part of the routing is done in the other die. Instead of doing routing like this, you do routing in the other die and come back. In other words, the bottom die is lending this metal layer to N3. We're borrowing and lending metal layers from different dies, my neighbors. We're sharing metal layers. That's how the name came from, metal layer sharing. You don't need to do routing in your own die. You go to the other die and do the routing and come back. Why is that useful? It is useful when this part of your N3 is so crowded, you cannot find any space for routing. In that case, you don't have any other choice but to go to the other die and do the routing and come back down. So this is quite useful in fighting routing congestion in 3D IC, which is a big problem in 3D IC, by the way. Not only that, this metal layer, M1, has very high resistance. But this M top is very low resistance. You see, delay is much better with this connection than that connection. Of course, you have to factor in the costs involved in this vertical via stack. But if doing this is better than doing this, then you might as well just do it this way. So this is metal layer sharing that we think is quite unique opportunity in 3D IC routing. Now, metal layer sharing, of course, there is a price to pay. So N3 needs a pair of face-to-face bonding, right? So you will see a lot of face-to-face paths used, even for memory logic folding. Because memory logic, number of connections that you need between memory and logic is just a 32-bit address, 32-bit data, no more than a few hundred. But then we're using a lot more than a few hundred, 37,000, because we're doing metal layer sharing like crazy. So that, of course, is the grand summary. So this is the 2D design. This guy. And then these are the second and third column. And comparing all these 3 designs, by the way, this is placement and that's routing, in terms of the same kind of metric. Performance, power, area, thermal, and IR drop. So here, unlike the other case, where all the performance is the same, all the performance is different. Because here my focus is performance. I'm not doing ISO performance power comparison. I want to make sure that my chip is working as fast as possible. Right? And then what I was able to achieve, right, is with 2D design, Maximum speed I was able to achieve was 630 megahertz, but then 3DIC 1.2 gig. It's almost 2x improvement on Fmax performance. Your chip runs 2x. Why? Because why is it shorter? Why the laser smaller? Folding reduces wire length very naturally. I showed you with a paper folding example, right? That's why Huawei said, okay, folding, right? And stacking, of course. If after fold, you have to stack. Now, there is some price to pay to enjoy this performance gain, because if you run your chip faster, your chip, consumes more power, so power consumption does go up. Okay? But then your chip is half times smaller, temperature does go up, right? And then IR drop, which is supply voltage drop, seen by all the transistors in the whole 3D IC, because long power, current delivery path will incur voltage drop. 3D IC, right? There's more IR drop trouble because the chip size is half of the 2D. The number of power ground C4s that you can add to your footprint reduces by 50%. Simply all these C4 bumps that deliver power externally to the chip, you have half of that. So you get more trouble. But you still have to feed the same number of transistors sitting in both tiers. The power delivery is indeed a grand challenge in 3D IC. And we see the impact of that here. Now, we did another study with the same design, but this time, I made all the performance the same. That's just like what I did with Intel, right? ISO performance power comparison. So all three designs are running at the same speed, and we're comparing the power. So here we did see the 3D IC gave you power saving, healthy amount 20%. Again, we saw this happening with the Intel case. We are seeing again this with Samsung's case. Again, why is it shorter? That gives you a lot of happy news. You can use it to improve performance, or you can use it to reduce power consumption. Because you're running your chip at low speed, the temperature gets better, although slightly worse than 2D. IR drop also improves. Now, in all of our study, we were always able to beat this commercial 2D with 3D IC. Right? We're always able to beat this commercial 2D with 3D IC. We're able to beat commercial 2D with 3D IC. This is commercial 2D with 3D IC. Isn't this natural? If your 3D IC is worse than 2D, why the heck do you do 3D IC, right? But achieving that was not easy. Being able to beat commercial 2D with 3D IC was not easy. It took us like almost 2 decades to be where we are. Why? Why did we take 2 decades to be able to beat commercial 2D with 3D IC? It's simply because design tools for 2D IC is so powerful. Chips that you guys use every day were designed with the commercial tool to give you this. This design tool is developed over many decades, 4 decades plus, with hundreds or even thousands of engineers working day and night at Cadence and Synopsys and Siemens. It's simply not easy to beat this result with 10 PhD students and 1 advisor. So how did we improve our role so we can beat these guys? We can beat commercial tool, and we can beat commercial tool. That's the next topic of my seminar today. Okay? So before we talk about that, I wanted to close this first portion of my talk out of 3 with some opportunity for new research. Okay? So what you see is what I have already achieved with my students and my sponsors. But what needs to happen? We made a humble first step. I will never say the problem is solved. 3D IC folding design is done. We have the ultimate solution. Heck no, no. We just took the first step. There's a lot more to be done. The first is EDA tool itself. I'm going to tell you about all those EDA tools, how we develop the tools. We see a lot of limitations still. So we will keep on working, and I encourage Fudan to join me in improving 3D IC design tools and LogicFolding tools. I know Fudan has invested a lot and have maintained such a big group in EDA. 3D IC EDA, trust me, it's very, very hard. There's a lot we can do together. First thing is improving EDA tools. Second is this. So what do I mean by better RTL? The architecture that we use to do LogicFolding. All these 2D designs that you saw. This design and this design, the architecture, the RTL code, right, is written for single die implementation. The architecture is 2D aware architecture. The RTL code is written to work well when they are side by side, not on top of each other. Now, what are some of the examples that you don't need if you do 3D IC? So for example, in 2D IC, memory access takes quite a bit of time. So if you have a cache miss, going to the last level cache and then fetching the data takes many clock cycles. But if your memory is stuck right above your logic, access latency, single cycle, right? What does that mean to architects, right? If you are doing architectural research, right? You know that there are things that computer architects do to hide the latency of memory access by doing out-of-order execution. You don't execute your instructions in the given program, but you shuffle and execute some instructions before the other, because these instructions have nothing to do with the memory fetch that you initiated before. Branch prediction. You wanted to predict the answer to if question, so you can start fetching the memory early on. You do all this because bringing data from memory takes long into the IC. So the architecture is built to cope with that. But in 3D IC architecture, you may not need that, because bringing data from your last level cache, you can do it much faster than 2D. What that means is your RTL code can be re-optimized with the stacking in mind. But I never had access to those 3D aware architecture. So if you're doing architecture research, let us work together. There is a way you can contribute a lot and build true 3D architecture that benefits from stacking logic and logic, memory and logic. And same thing, with manufacturers. So I feel the need to talk more closely with foundries, because foundries are the ones who are manufacturing my chip. After I tape out, these designs to manufacturers, they will start making, these chips. When they're making these chips, they may say, "Hey, Sung Kyu, I don't like this. I don't like this. It's so hard to manufacture. Please avoid bringing yellow dots closer together. Spread them more apart, or create more regular type of yellow dot placement." which will be a lot easier to manufacture. You see, manufacturers will give designers a feedback on how to improve manufacturability of your 3D IC. And based on that feedback, we want to be able to optimize our design to improve manufacturing. DFM, right? Same thing. After you finish your design, okay, maybe your timing analysis will tell me that this R3 wire resistance is so crazy, it shows up in every critical path. Then you can maybe call up SMIC and say, folks, we hate M3 resistivity. Please use different material or different process recipe to reduce M3 resistance. Hey, SMIC, listen, M5, maybe you can, use a cheaper material because M5 resistance is not too bad. Via pitch. So you can give feedback back to manufacturers based on your design analysis, you see? So your designers and manufacturers can talk with each other and then help each other and create win-win scenario. That is under the topic of design technology optimization. And of course, there is multi-physics, cooling and power delivery and test. All these are as important. Being able to model die-to-die variation because your top die and bottom die, the transistors don't behave exactly the same. Because your top wafer may come from, vendor 1, and then bottom, wafer may come from vendor V. Their devices look identical, but then the performance may be different. So die-to-die variation in 3D IC is something you definitely have to model. On and on and on. There's a lot to be done. And I'm pretty sure that smart people at Fudan University can contribute a lot because right now Huawei needs a lot of help. And Dr. Huang is listening to everything that I'm shouting here. He is in charge of EDA at Huawei. Now, before I move on to my next part, is there any question I can answer? Yes. Okay, great. So yes, the question is, how much is the delay caused by the elevator compared with the delay caused by the wires in the same die or gates, right? So again, that's an excellent question, right? So now the delay from one transistor to another transistor, I think I have a nice photo image to describe this. So delay from here to there, right? Is still less than 1 clock period, but it's significant. Significant. Maybe depending on where the location of the transistor is, could range from tens of picoseconds to even 3-digit picoseconds. Depending on the size of the buffers that you use to drive this signal. Right? And then based on which technology node you're talking, maybe the gate delay it could be compatible to this delay, or gate delay is much smaller than this delay. So it all depends, right? But then one thing that is for sure, right, is this delay is not free. It's significant. Yes.
Thank you, Professor Lin. I'm very excited about your talk. Okay. And I have 2 questions, one general and one specific. So do you think that we need extra inputs in the total flow of IC design? Because I noticed that you talked about enhancement of the current inputs like PDK and the library and the standard cells. In the partition side, I think do we need, I guess, extra inputs for top partition, no matter it's in RTL level or in physical level? Because you mentioned that, for example, the high density part of 2 dies, if they don't overlap, they can share each other's top metal, which is quite great. And do we need, for example, do we need this kind of inputs as an extra input for synthesis and partitioning? And the second question is,
So before we talk about the second question, I wanted to understand that single word I'm still missing. So do we need extra
inputs, for example, SDC, library,
inputs?
input. Yeah.
Inputs.
Input like SDC library, standard cell library.
Oh, I see. That's what you mean.
Yeah.
Right. So we haven't talked about the full, design flow yet, design algorithms yet. But then if you want to do middle layer sharing, right? It's not okay. So we need 3D version of PDK. So you have to extend your PDK to be able to do middle layer sharing, and then you need a 3D version of cell library to be able to place your transistors or gates in two tiers. So I will have a slide to tell you all about extension of PDK from 2D to 3D to do routing and placement. But again, that slide is coming up later. But then to give you a quick answer, yes, you need to extend your PDK to be able to handle 3D IC design. Right. And then your second question is?
Yeah. One follow-up for the first question, that who do you think should take more responsibility in the partitioning of different dies? The front-end designer, architect, or physical designer?
So that's a very interesting question. When you do tier partitioning, who should be more careful? Is it front-end designer, including architects, or is it going to be physical design?
Yeah. So it's like more cooperative. Different step, say, focus on different level of partitioning, like data path partitioning, block partitioning, sub-block partitioning. Yeah, please.
That's a great question. So, of course, the answer is going to be both, right? So there are things that architects can do to help better partitioning. So, for example, you look at your RTL code, right? And then at your RTL level, without any synthesis or PNR, you can do tier partitioning of RTL modules. Just by looking at RTL code, RTL has a hierarchy, right? There's a top level modules, and then inside one module, you have sub-modules, and sub-modules will have sub-modules, right? So you can definitely draw this tree of RTL hierarchy, right? Then you can do tier partitioning of these modules at a certain level. You draw a cut line that peers through some sub-modules and sub-modules and their sub-modules. Right? So this tier partitioning can be done at the RTL level. Then also your tier partitioning can be done at the physical design level. After you do synthesis and after you see all the gates in all these modules, you do bottom up basically. Gate 1 go to the top, gate 2 go to the bottom. So you can do tier partitioning in bottom up fashion or top down fashion. And you can share information between these two. So for example, right, after you do some partitioning at the RTL level, right, when you make any decision at the RTL level, the amount of information available is very scarce, so very rough, right? You don't know whether putting this submodule in the top or bottom will improve your PPA by how much, or reduce hot spot temperature by how much, unless you do physical design. Right? So then you can ask your physical design guy, hey, I did this RTL level partitioning. Do a quick layout and give me feedback, right? Same thing. I'm doing partitioning at the physical design level, right? But I see that this RTL module causes a lot of trouble in timing. So then what I can do, right, is call up your friend who is doing architecture. Hey, you wrote the RTL module? You got to fix it, man. I hate this, so that you can give your feedback to even improve your RTL partition. See, so both ways are possible.
Yes, thank you for the question. And I bet there should be more tight cooperative and even some specific tool for this, because I am a sign-off engineer. So when we do sign-off, we give feedbacks to the front-end guys and tell them that, oh, we cannot meet timing. Please add one more cycle by insert one register. It's easy, it's quick, but if we need to break up the data path between two dies, it costs much more than 2D chips.
Yes.
Yeah. Originally, it only added one more cycle, but maybe you need consider much more hybrid bonding, pitch, density, much more things. So yeah, it's not a question. It's just some of my thoughts. I think it will be very interesting and important.
Right.
Yeah. So yeah, I think you have answered my second question. Thank you.
But my point is, don't be afraid to fold up data path. You may be concerned that if the moment you start touching up your data path and fold it, it'll get worse. Actually, no. No. I mean, we've seen in many cases where data folding, if you do it right, will improve your performance. Because wires are getting short. You just need to do it better, right? So you need more sophisticated algorithms, but don't be afraid to fold it into two.
Thank you.
Mm-hmm. So what I'll do, I'm just going to move on, right? And then, of course, I will have additional Q&A time in the end. So let's talk about EDA tools. Now, so far, I told you about what you get by doing folding. Then my next part is, how do you fold? Not you, the human. How do computers fold, right? So we're going to approach this problem from two different angles: traditional approach and also AI-based approach. If you have just one here, 2D IC, right, doing this design automatically is already done. You can go to Cadence, Synopsys, Siemens, and other startup companies in Shanghai. I visited one on Monday. They're doing fantastic job. You can buy these tools today and then get this done. The 2D IC design tools will do two things. It'll do placement and it'll do routing. By the way, everything I discuss is digital. I don't touch anything about analog here, okay? And then I'm focusing on physical design, placement, route. I'm not talking about synthesis. So 2D IC tool is available. You can buy it. 3D IC, no. Tool is not available, and it's much harder. Why? If you have a two-tier 3D IC, you need to do placement for tier 1, placement for tier 2, and you need to do routing for tier 1 and routing for tier 2, and then these two dies need to be connected with each other. Here in 2D IC, you're drawing 2 paintings. Here in 3D IC, you need 5 paintings. And these 5 layouts need to be co-optimized all at the same time. Anything that you do with the top tier placement will have impact on the other tier too. You need to look at all those 5s. The moment you change the bump location of that connection in that 3D net, it'll affect the delay. You need to look at all 5 layouts simultaneously. This is much harder than just dealing with 2. Now, I get this question a lot. If you have some experience of doing 3D IC design, you might have heard these products. Cadence is selling Integrity 3D. Synopsys is selling 3D IC Compiler. Siemens is selling Expedition. And then they say, oh, our tool does everything, right? Our tool does 3D IC design. Just buy our tool, you're done. My answer? That's not true. That's not true. Integrity 3D IC, 3D IC Compiler, Siemens Expedition, we have access to all these tools at USC. They are not chip design tools. They are package design tools. How is chip design different from package design? Chip design, you design chips, what goes into your die. But package design, you design the package, not the chips themselves. In your package, you will have multiple dies, that are routed with the package traces that you can design with these tools. The reason why they call their tool 3D everywhere, right? 3D here, 3D there, is because these tools can handle interposer, silicon interposer, organic interposer. Because some people think that H100 from NVIDIA, HBM from SK Hynix, mounted on a silicon interposer as 3D IC because they're stacking GPU on top of interposer, they're stacking HBM on top of interposer. So hey, stacking, right? So hey, this is 3D IC. No, we have a different terminology to call that. We do not call that 3D IC. What we call that 2.5D IC. So all these tools are 2.5D design tools. But for some odd reason, they never call their tools Integrity 2.5D, Synopsys 2.5D compiler. They call it 3D, 3D, and 3D. In my perspective, if you have a 3D IC design, right, your 3D IC design needs to handle the fact that you have multiple transistor tiers. Not just one, but two. You have top tier device level, and then you have the bottom tier device level. Even today, Innovus, ICC2, Aprisa cannot handle multiple device tiers. In the entire DEF file, you should only have one tier of transistors, not two. So my answer is 3D packaging design tools? Yes, it is available. That's what NVIDIA uses to tape out H100 and all these AI chips that you guys are using. 3D IC tools are not available. So what does that mean? I want to design 3D IC, and I want to design 3D IC that beats 2D IC. Commercial 2D IC, right? Not just any 2D IC, but I want to beat commercial 2D IC with my 3D IC design. Otherwise, industry will never care about what you're doing. I mean, if your 3D IC is worse than my commercial 2D chip, who's going to care? I know Huawei is a nice company, but then they cannot, bring that chip to their next phone, right? If it's worse, who's going to buy it? So we've been struggling a lot on building a tool that gives you high quality design 3D IC. And this is how we do it. So we named this tool Compact 2D. The way this works, right, is actually quite simple. So what we do, we buy 2D tool and do 2D design. And so that's our starting point. Of course, doing this, we already have a commercial tool that does that, right? Then what I do, right, is I do compaction. What do you mean compaction? All these, cells in 2D IC design or modules in 2D IC design, if you do placement, you know the XY coordinates of all these, right? What you do is you multiply 0.707, which is 1 over square root of 2, all those XY coordinates. And then this is what happens. The scaling factor of 1.707, right? 0.707 is compacting this design into half of the footprint. Why half of the print? Half of the footprint? Because in the two-tier placement, the footprint of the placement is half the size of that, right? So I wanted to decrease the footprint of my design into half of the footprint while not moving around these things. I want to make sure that the fact that this guy's above this, I want that there, right? I want that these two guys are close with each other. I want that there. I want that this and that are far away from each other. I want that there. The way you make that happen is by just compacting your design. But if you compact your design, you see a lot of overlaps, right? What do? We partition this design into 2 tiers. Hey, you go to top, you go to bottom, you go to top. This is what you get after tier partitioning. And you'll see that some of these cells still have overlaps. You legalize it. Shift around, so get rid of the overlaps, and you're done in 3D IC place. This is compact 2D, and for some good reason, we got the best paperwork from IEEE TCAD. Simple idea, this works well. Sometimes that's all you need. If your idea is too complex, people may not, like it. Very simple idea, but works well. Oh, that's what you need. So compact 2D is what we did to get the placement. Next, we do pin 3D. I'm so thankful to Professor Jiang Wang for the university who implemented this and then made it public. So you can download the source code of his implementation of this work. And we verified it ourselves. It was 100% correct. Now you guys can download this tool from his website, okay? Now, pin 3D, first of all, we do routing for 3D IC. And there was a question about, what kind of input is needed to use this? And I said, PDK needs to be extended to be able to do this. Now, what's happening here, right? Again, my strategy, I do not want to reinvent the wheel. I do not want to write a new program that beats Microsoft Office. There's just no point. I cannot write an OS myself and beat Windows. I will use Microsoft Office. I will use Windows. I will use Cadence. I will use Synopsys, but use it to do something new. So here, what I'm going to do is to use their 2D router to route 3D IC. Again, one more time. I want to use their 2D IC router to route 3D IC. You're like, is it possible? Yes, it's possible. How do I do that? Now, first of all, your metal layer stack needs to be extended. Because if you have 3D IC, you have metals for the bottom tier and you have the metals for the top tier, right? And if you do face-to-face bonding, the top tier metal needs to be flipped. So that's exactly what you see over here. This is M1 to M top for the bottom die, and this is M top to M1 of the top die, right? To create face-to-face bonding scenario. So this, you need to extend tech LEF, interconnect, LEF file in your PDK into 3D. Then what you also need to do is for each cell in your library, you need to create top tier version and the bottom tier version. Because if your cell is in the top tier, right, your pin is going to be here somewhere. If your cell is in the bottom tier, your pin is going to be down there somewhere. Right? For the same inverter, minimum size inverter, some inverters that are sitting in the top tier will have their pin in M1 of the top tier all the way up there, versus bottom tier will have that, right? So you need, cell library for the top and the bottom tier. So that's another input that you need, right? Now the third is, when you're doing routing, you are finished with placements. You know where all the pins are. And you would annotate the pin location into this double metal stack. So cell 1 pin is here, cell 2 pin is there, cell 3 pin is here, cell 4 pin is there. So all the cells, their pins are annotated into this 3D LEF. But then what you see here is 2D IC. This is not a 3D IC because all you have is just pins and cell, boundaries. You give this to a 2D router, NanoRoute from Cadence, what have you, right? 2D router will just work just fine, and it'll route these pins together. Then during the routing, it'll place all the back and line vias, And that specific via that connects the m-top of the top and m-top of the bottom, right there, that is the location of phase pad. After you're done with this, you get these three for free. The router gives you all these three for free, automatically. First, connection from logic to phase paths. Second, face-to-face location. And then memory or bottom tier to phase space paths. All 3D nets are routed automatically. And then their face-to-face locations are all automatically decided. It took us quite a bit of time to make this work. The idea is quite simple. 2D IC router routes 3D IC design if you do it this way. Another thing that we did, the Thai way implemented correctly, right, is timing optimization. You know, you have a target speed. I want to run this chip at 2 gigahertz, right? That means longest path delay has to be less than 500 picosecond. We learned that from your class, right? Now, to meet that goal, you need to add buffers. You need the size of gates. So that's time enclosure. You need to optimize your performance, improve delay, right? Now, again, I want to use 2D IC time enclosure engine to close timing for my 3D IC design. How is that different? 2D IC timing optimization engine can only handle one device tier. Okay? But 3D IC has multiple device tiers. And some of these cells have same XY. Z will be different, but the XY coordinates could be the same. Then if you merge your top tier design and then the bottom tier design into one DEF, one 2D IC design file, cells will again overlap. And then the moment a commercial tool sees cells overlapping, and this tool becomes very angry. It starts moving things apart and try to legalize your placement. I spent so much time, getting this two-tier placement done with Compact 2D. But the moment you merge these two again, the placement is destroyed. But I still need to add buffers the size of these gates to close timing with a 2D tool. How do I do that? Right? This is how I did it, and that's what Thai Wei implemented and posted on GitHub. So long story here, but then the main idea is this. You see the top tier cells and bottom tier cells? Okay, you go back and forth between top tier and then bottom tier. So you add buffers and size gates in the top tier. When you're done, you go to bottom tier and you do the same thing. So you go back and forth. But then when you're working on top tier, the bottom tier cells, you make them transparent. In other words, when you're working on bottom tier, the blue guys, I want to size up and add buffers here. The red cells that are sitting in the top tier will be projected to the bottom tier. They will share the same space. But then these red cells will become transparent so that you only see blues being active. And then when you're working on top tier buffering and sizing, you make bottom tier blue cells transparent. When you make cells transparent, the overlap is okay. Commercial tool says because they're transparent, they don't exist here. But even when you make your cells transparent, their pin locations are still alive. So for example, if you look at this N1 that connects this top tier and then the bottom tier cells, the entire 3D connection is visible even when you made red or blue cells transparent. In other words, when you're adding buffers and size gates, you see the whole thing. You not only see what's happening in the bottom tier, but you see what's happening in the top tier and then the connection to the bottom tier. You have the whole entire view of the whole 3D nets, the whole 3D pads. Just the cells are transparent. They're not affected. So this is a little hard concept. So if you get it, that's good. In any case, even if you don't get it, I mean, one thing that's happening that I want you to get out of this, right, is we found a way to use a tool that works for 2D IC to close timing for 3D IC. And the trick is, when you work on top tier, make the bottom tier cells disappear. But connection to it, you still consider, vice versa. Now, one of the big things that you have to do, right, here, to go from here to there, is tier partitioning. You got to partition your design into top and the bottom. That, there's no 2D IC tool that you can buy that does this. So you need to develop your own partitioner. So in case of Taiwei, Professor Wang used open-loaded partitioner, right? So what we did was this. Partition problem is very hard. What you do is very easy because each gate you go to tier 1, 2, 3, 4. So for each gate you have 10, 4 choices. Solution space is 4 to the power of 10. If you have 10 gates, but if you have 1,000 gates, solution space is 4 to the power of 1,000, which takes that many years. Nobody will live this long. Very hard problem, but it has a huge impact on electrothermomechanical quality of your chip. Now, the way we partition or design at the top and the bottom is. I told you we have some initial 2D design done. You split the 2D design into small bins. In this case, 9 bins. And then you go to each bin here. And then you split cells in that bin to top or bottom. Here, what we did, we used iterative improvement. What that means is you randomly partition this cell to top or bottom, right? And then you improve your random solution by moving cells from one tier to another. So that's the spirit behind iterative improvement. So which cell then do you move to the other tier? It's all based on the concept of gain. Right? So this gain can include how much number of connections you reduce or how much timing you can improve. So this gain-based change of your current solution from random to optimized is what this algorithm is designed to work. So based on this gain formulation, right, you then finish partitioning this, and this, and this, and this. So then after everything is done, then you're done with partitioning the whole design to top and bottom. Now, we didn't end here because this bin FM kind of sucks because we use MinCut as the objective. MinCut is not a very good way to make use of short vertical connections in 3D ICs. Instead, what we did was this. So 2020, we used a graph neural network and K-means clustering with unsupervised learning to do tier partitioning. We call it TPGNN, tier partitioning with GNN. Long story short, the way this guy works, right, is we model our circuit with a graph. Because circuits and graphs are very, similar kind of concept, where gates represent nodes, right? Nets are represented with edge in the graph, right? So after you model your circuit with graph, what we are doing, right? Each node in the graph will be represented with the n-dimensional vector. 128 dimension is what we use here. Then what we want to make sure, right, is the cells that need to go to the same tier, we want their vector representation to be similar. So if you draw the location of these points in the n-dimensional space, the cells that go to the same tier will be located similar in that n-dimensional vector space. Oh, what do you mean? You know, language model, right? All the tokens represented in an n-dimensional vector. And if these tokens mean similar, right, then their vector representation is going to look similar, right? That's exactly what natural language processing is all about. Representing words with n-dimensional vector, and then their vector representation becomes similar if their meaning is similar or related in a long sentence, right? So we're doing the same thing here. Now, the way we ensure that the vector representation of the cells going to the same tier is similar is by using this loss function. Now, this loss function has two components. The first loss term ensures that if your cell, a pair of cells is connected with the same net, then their vector representation should be similar. So vector product of two vectors, and a sigmoid and a log and a minus, okay? If they are similar, this whole loss function is minimized. Now, second, term in this loss function, make sure that if a pair of cells is not connected directly in the graph, their vector representation should look different. So what happens here is for a given node V, you're looking at negative sampling. You visit V, and in your sample all nodes that are far away from V, negative sampling, right? And then we want to make sure that this far away node in my graph, right, should look very different from me in terms of n-dimensional vector representation. And then you keep on iterating between this, right? So going forward, calculate the loss. Based on the loss, you update your vector representation with gradient descent. Iterate this multiple times. And when you're done, you reach a point where you achieve your goal, and then all the cells that go to the same tier will have similar vector representations. Then what you do is you start doing K-means clustering. K-means clustering, based on the location of the centroid, will draw cells in a similar location in n-dimensional vector. So you form a few clusters, and then eventually you start merging the cluster into tiers until you have two big clusters left. Then you're done clustering. And this is how we do tier partitioning. Either we use FM-based approach, the traditional approach, guided by gain concept, or we could have, we also have done it with GNN, graph-based learning, and differentiable loss function. Turned out this was much better than the other one. Now, the last topic on EDA, right, is 3D IC placement. Now, 3D IC placement is similar to tier partitioning, except that now 3D IC placement, you determine X, Y, and Z. Very tough problem, but it's much harder than just determining Z only. Now, the way we solve this, right? So this is traditional approach where we decide X, Y first, and then Z next. This is so-called pseudo 3D. XY first, and then Z next, partition last. That's what compact 2D is doing. Not X, Y, Z all at the same time. X5 first, and then Z. This is pseudo 3D. Now, but I also have done some work where I calculate X, Y, Z all at the same time. True 3D placement. So the way my true 3D placement of deciding X, Y, Z all at the same time, instead of X, Y first and then Z later, is I'm going to start from some initial placement. I'm going to improve this initial placement by updating X, Y, Z. So that's a very typical way of solving EDA problems in physical design. You start with some solution and you keep on improving until you cannot. So here my approach, right, is I'm going to use my pseudo 3D to come up with initial placement. I'm going to improve these placement by updating X, Y, Z together using AI. This is how I do true placement, which is improving X, Y, and Z as initial point. Okay? So this is how I do it. Very crowded. But then, I'll do my best to explain this as simple as possible. So we use two main techniques. Going forward is done with the Siamese unit that predicts post-route congestion from given placement. This is what's happening in the forward calculation. And then backward calculation is calculating loss from this post-route congestion map and then minimizing this loss by updating X, Y, Z coordinates. So this forward and backward pipeline is what we develop to improve X, Y, Z all at the same time. Now here, our goal during X, Y, Z improvement is performance and congestion. Congestion turned out is a very important objective that you must consider during placement. Why? Routing becomes very much challenging in 3D IC because your chip is half of the size, pins are closer with each other. Your routing track is being used by signal and power and clock. So all these routing tracks in all metal layers are very, very crowded. Routing congestion becomes really headache. And you don't want to wait until routing is done. You want to address congestion even during placement, early on, right? So our loss functions have those congestion-related terms. So this is how we calculate congestion per routing cell, G cell, from this predicted routing congestion map. And also another loss function that's differentiable that looks into number of connections between the top and the bottom tier. We call it cut size. And then this overlap loss function, right, is calculating the amount of overlap, between bounding boxes that estimate wire length after routing among different nets. And then displacement is calculating how much you move the current location to a new location, because you're changing the current X, Y, Z to X prime, Y prime, Z prime. You don't want to move these cells too much, because if you do that, your timing gets screwed up. Right? So all these loss functions are differentiable, and then they're combined and then used to drive my backward propagation or my gradient descent algorithm. We'll pick a few cells and tackle their X, Y, Z coordinates so that the new X, Y coordinates will reduce this combined loss. Now, that's what happens during backward propagation. And forward, what's happening here, right, is that I need more accurate assessment of congestion. So we started with this Rudy map and pin Rudy map. What do you mean Rudy map? Rudy map is a very popular way of predicting routing congestion for 2D IC placement. So we use this Rudy map and extend it to 3D and use it to see if Rudy can predict routing congestion very accurately in 3D IC. It turned out we were very disappointed. We were very disappointed because the Rudy map prediction for routing congestion for 3D IC was very off. So what we decided to do is to improve this routing congestion prediction from a given placement, not by using Rudy as is, but then by using this Siamese network that we trained with trained data. Yes, we did use supervised learning here. So the input to this Siamese network that has 2 heads and 2 sets of feed, by the way, conjoined twin, right? We call them Siamese twins, right? Has 2 heads and 2 sets of feed. So 2 heads work nicely for us because we have 2 tiers, top tier, bottom tier. And then this combined conjoined part in the unit, right, can be very efficient in modeling the interaction of the top tier and the bottom tier, because the place where you have lots of congestion in the top tier, right below it, there's a chance that the congestion will also be bad. So this interaction between top and the bottom tier is very well modeled and trained in this conjoined part of it, but then eventually you have to split and predict routing congestion for the top and the bottom. So this Siamese unit just works perfectly for us. So we model all the parameters used in convolution, deconvolution, right? By using trained data that we created. So once you train this enough, then going from Rudy to post-route congestion was done very accurately. Okay. So that's some aspect of EDA tools that we developed that enabled folding. Any question? Yes, sir.
My guess is there some tool that can so if there's some 3D library, 3D DK, some tool can convert 2D RTL to 3D RTL by the tool, that because all the delays are available, right? All the information are there. So in the arc level, the RTL can be converted automatically by 2D to 3D.
Wow. Oh, that would be awesome if there is an automatic converter that converts 2D RTL to 3D RTL. That's very hard. I have never seen anything like that. Yes, it's a very tough research problem. Very tough. But again, there's a benefit, like I said, right? Architecture designed for 2D IC with stacking in mind, right? Will have very different kind of organization of functional modules than what you have in the 2D IC. So to train that model, you need to create trained data. So in the beginning, right, you need to hand design, hand optimize your 2D RTL to 3D RTL by making use of all your knowledge on architecture. Then if you have enough of those data collected, then you can train the model so you can convert a new 2D RTL to new 3D RTL. But that, if that exists, that will be a game changer. Right, so moving on to the last part. So again, a lot of things happened in early 2010. So 2010, I received a phone call. They don't use email. National Security Agency of U.S. government. It's pretty much compatible to FBI and CIA. These guys called me up and say, Sung Kyu, I know you're doing 3D research. I don't need papers. I need a chip. Can you make it? I don't need papers. I need a chip that works, that runs applications. Sure, okay, I'll do it, just if you give me enough money, right? So they did give me enough money to do this, right? Then I had this question. What do you want me to demonstrate? What's the purpose of this? I thought they would say, power saving, performance improvement, die areas, reduction. No. Show me this. Show me that. Bandwidth. What do you mean bandwidth? How much memory content you can read in 1 second? Terabytes per second. Gigabytes per second. Show me how much memory bandwidth you can achieve with die stack. So we did this work, and then we published this work at ISSC 2012. This is a cross-sectional view. We cut this whole 3D IC and then revealed the die. By the way, so you'll see one bare die that looks like this, and then its packaged version. You will also see a larger chip that is not packaged. So I'm going to talk today about the smaller chip. So please don't try to open it because I please don't open it. So this 3D IC has 2 dies bonded. It's not just 1 die. If you look at the thickness, it's quite thick, right? So the top die is all the logic cores, 64 cores, and then the bottom die has the memory. But the bottom die is not thin. This is like 750 some micron thick, but then the top die is thinned to 12 micron. And then these 2 dies are face-to-face bonded. These are face-to-face bond pads. And then this is, a top-down view of 1 core. We have 64 of those. I formed a team with 3 professors. Back then, when we started working on this, I had Sean Lee and Gabe Lowe as, architecture faculty at Georgia Tech. So 3 of us formed a team. And then 15 students have worked on this. Now, the device technology is 130 global foundries. And it runs at 1.5 volt, consumes 4 watts. The cores run at 277 megahertz. The area is 5 millimeter by 5 millimeter. How much money did I spend? 0. Thankfully, because DARPA, US DARPA, has paid for the MPW to run, right? So, happy, if you do it for free, right? But then the area that I was given was only limited to 5 mil by 5 mil. I could not, pay more money to get a larger area because there's a lot of participants. Okay? So 5 mil by 5 mil is my footprint. So with that, I was able to, fit the 64 cores, 8 by 8, and then 256 kilobyte SRAM. And then the maximum data bandwidth we achieved by running the real app was 70 gigabytes per second. So you may say, okay, so is 70 gigabytes per second good or bad? I mean, if you see a number, you don't know if this is good or bad until you compare the number with something else, right? So I'm going to compare exactly that with other chips and show how, good quality this data method is. In any case, my bonding technology, the face-to-face bond pads, at 5 micron pitch. 14 years ago, 5 micron was already doable. In other words, 5 mil by 5 mil chip, bond pitch is 5 micron. How many 3D connections can we have? Maximum number? 5 mil, 3D bond pitch is 5 micron. How many of those can we have here? 5 mil, 5 micron, you can have 1,000 here, 1,000 here, altogether 1 million. Even this small footprint, you can have 1 million vertical connections. You can manufacture that chip even 14 years. I was very surprised. My chip worked. It executed all the apps and produced correct results. We did all the testing. Now, out of 1 million possible, we only use 51,000 of them. Okay? So we still have a lot of wasted face-to-face connection, but still, this was good enough to demonstrate this much bandwidth. Now, our architecture. So there was a question about how to auto-generate 3D RTL, right? Or how do you optimize your RTL architecture to work better with 3D IC? Here is a perfect example. This architecture is 3D optimized. Why? Because we issue 2 instructions in 1 clock cycle. So this is VLIW. One instruction involves ALU operation. And then the other instruction as access memory in the other tier. And then this memory access is done in 1 stage in the pipeline. In other words, memory read and write is done in 1 clock cycle, not a few tens or a few hundreds of clock cycle. You can access your memory 1 clock cycle, every clock cycle, because you're issuing 2 instructions. And the instruction, right, is accessing memory. In other words, you can keep on issuing memory instructions, and this memory instructions in every clock, every pipeline stage, keep on accessing this. This is the ultimate, thing you can do. Every clock cycle you access memory and bring data. Here, I didn't have to use, branch prediction, out of order execution. I didn't have to kill any pipeline stage waiting for data. None of those are necessary. This is truly a 3D architecture that's optimized based on memory logic stacking. Now, we wrote 8 applications, including median filter. We didn't have a compiler, so we did assembly code. My student has done some of that. And then this median filter gets rid of noise in the image. This app consumes 4 watts and then achieved 63.8 gigabytes per second bandwidth. Now, this chip needs to be designed and taped out. So design and this design is done with our pseudo 3D flow. So this is the bottom tier memory, and that's the top tier logic. Memory tier design was done with the memory compiler that were given by Global Foundries. But then the top tier logic is done with our pseudo 3D flow that looks at the bottom tier and then the top tier and the bottom tier, and then optimize 3D NAND delay and build 3D IC clock tree. See all of those. So comparison, right? That's our number based on the real chip that you guys saw. This is, wow, NVIDIA 100. So how dare I compare with NVIDIA 100? I dare to compare because numbers are meaningful. The NVIDIA 100 done with the TSMC 4, the GPU. HBM is done with 10 nano, SK Hynix. This chip area is 814, not 25. This whole NVIDIA GPU in the middle has 15,000 CUDA cores that run at 1.6 gigahertz, right? And then every clock cycle, this GPU reads 1,000 bit from 6 HBMs simultaneously. So, data bandwidth in terms of, number of bits per clock cycle you can bring from memory is 6,000. But my chip is 2,000 already because we have 64 cores, and all these cores can bring in 32-bit data every clock cycle. Right? It's 2,000 already. We're getting close. Now, if you look at H100, catalog, they say this whole chip achieves 3.35 terabytes per second. Yeah, okay. Commercial tool, much bigger, much more advanced, much better than my 0.7 terabytes per second, 0.07. Now, AMD V-Cache being sold from 2022. This, the whole chip is done with TSMC 7. The chip area, right, is 80 millimeter square, 8 Ryzen core, 4 on each side, running at 4 gigahertz. Every clock cycle, last level add to cache to CPU on the bottom, you can fetch 4,000 bits. And then AMD VK says, if you buy our chip, you get 2 terabytes of data per second. All right. First of all, number of bits per cycle, we're getting very close. 3 professors, 15 students, hundreds or thousands of engineers at NVIDIA. Right? Again, similar number of engineers at AMD. Now, yes, this number is quite different, but keep in mind, my chip is done with old node, smaller area. So if I do have access to AMD environment where I have access to TSMC 7, and I have a larger area, 80, same as this, not even this, I can fit 50,000 of my cores instead of 64. And then I can run this chip at 4 gigahertz. And then this is how many bits per clock cycle I can bring from memory. Logic. Much, much better than this. Now I can convert this to terabytes per second instead of bits per cycle. This is my terabytes per second number. If I re-implement my 3D Maps chip, 7 nanometer with that chip area instead of 130, that area. Now, this I know is not apple to apple. Of course, my architecture cannot run, all these transformers and all these fancy algorithms that H100 is capable of running. But one thing I do want to point out, though, this and this is why NSA paid me to do. 3DIC can give you very good data bandwidth. You stack memory on logic and re-optimize your architecture, and then you have access to state-of-the-art EDA tools. Last slide I have is this. It's exactly what Huawei is trying to achieve here. Old node 3D IC beating new node 2D IC. Legacy node 3D IC beating advanced node 2D IC. Now what you see on the left-hand side is my chip, 130. So yes, we had a 0.07 terabytes per second, but if I have as big as an area as this NVIDIA chip, I can increase my data bandwidth by that much. And this is what you get currently with the RTX 4090 and DDR6 done at 10 nanometer. That's the data bandwidth you can achieve. So my point here, right, is trying to deliver data bandwidth of the advanced node. You can do it by stacking and logic folding with old node. Is there a problem with this? Okay. Right. So yeah, I'm done basically. So how long my dream comes true? If this happens, I'm gonna buy this phone. I'm gonna come to China and buy this phone because I've been waiting for this moment forever, for my entire career. I wanted to see 3D IC, being used in my cell phone. Then I can show this phone to my daughters. This is what your daddy has been doing, right? I have two daughters and going to college. They were always asking, Daddy, what folding-based design? I talked about how folding and folding and folding keeps on improving the quality of your, design. And then to do that, though, you need a lot of help from EDA because this digital design, you don't do it hand, right? You need algorithms to do this automatically. That means you need all, sophisticated algorithms that make this design possible. You can use traditional approach or AI-based method to do this. Now, 2D test chip that I did indeed show that data bandwidth can be very high. If you optimize your architecture, if you do your design with the advanced EDA tools, and then manufacturing technology is still available. You can do you were able to do 5 micron pitch 12 years ago. This you can do a lot better. Now it's time to invest a lot more on EDA, design, and folding, and talking to foundries. Thank you very much.
Yeah, really thanks for Professor Lim's distinguished talks. And those numbers are very promising. We still have some time for our audience. We have some opportunities to ask questions to our Professor Lim. Do you have any question? If you have any question, please raise your hand.
Thank you, Professor, very much.
Oh, you don't have to stand. You can just sit down and just ask me questions. That's okay.
So, thank you, Professor, very much for all those practical 3D IC examples. And I'm a student still studying in this region. So I have a question that might deviate a little bit from the process that you're using in most of your examples, which, as far as I know, is hybrid bondings. And I encountered a problem with the placement of TSVs, however. So how and when, the problem is how and when are the locations of the TSVs decided? So are they decided after the logics are folded, or are they placed, decided before the folding is performed, which I believe is what in the case of hybrid bonding, their location is decided after the logic is folded. So why I think this problem is important is because deciding their locations, the location of TSVs prior to the placement will considerably shrink the design space. So it adds a lot of limitations to our logic folding. And but if it is performed after the logic folding, as you mentioned, it will create irregular placement, which manufacturers dislike. So another problem is that, do you think this problem will be a key limit that causes hybrid bonding to always outperform TSVs forever, even though TSVs provides an opportunity to stack more than 2 tiers together, because TSVs either will limit the design space substantially? Thank you very much.
Wow, I can tell that he's working on this problem, right? So based on the depth of his question, right? So TSVs, if you have a 2-tier 3D IC, don't use TSVs for tier-to-tier communication, because face-to-face pads don't occupy any space in your transistor tier, right? So if you have a 2-tier, definitely go for face-to-face in hybrid bonding. Don't do face-to-back, because face-to-back will use TSVs for data-to-data communication. And TSVs are much bigger and share space with transistors, right? But like you mentioned, right? If you have more than 2 tiers, right? 3 tiers, you're doomed to have face-to-back. Then you have to use TSVs for tier-to-tier communication, right? So I would assume that your question is based on that fact. You have more than 2 tiers. Then you will have TSVs, occupying your space, right? So in that case, yeah, I mean, in that case, you definitely want to minimize the number of TSVs used for data-to-data communication, because TSV itself is big, but keep out zone because you don't want to bring your transistor too close to your TSP because mechanical stress changes the mobility of the transistor nearby, right? So, so you don't want to, leave some keep outs, and so each TSP occupies humongous space in your transistor tier, right? So during your tier partitioning, make sure you minimize the number of TSPs that are required, okay? And then these TSPs, if you have to use TSPs for the theoretical communication in more than 2-tier 3D IC, you want to form regular arrays. You don't want to use irregular TSP placement, because irregular TSP placement causes a lot of trouble in mechanical integrity. TSPs themselves cause a lot of stress because of CT mismatch between copper TSP and a silicon substrate, right? So you do want to make sure that your TSPs form an array. Now, when do we form array? I think you can pre-place these TSPs, form array, before you even do placement, right? So you pre-place all these TSP arrays, then space in between, you can do a standard shell placement, right? So that's how I see how I see TSP management being important. If you have a face-to-back bonding, if I were you, I would place TSPs before placement. Now, even 2-tier face-to-face, you still need TSPs in the bottom tier. Why? Because you need to deliver power from C4, and you also need to deliver I/O signals from C4. So you will, even if you have face-to-face with hybrid bonding, you will need TSPs in the bottom. And they will occupy space in the bottom tier and share space with transistors, right? So in that case, what you want to do is to, again, pre-place these TSPs, right, that deliver power, meaning you want to do PDN routing first. Lay out all your PDN routing and TSP landing pads for power delivery, TSPs. Then with the space, remaining, then you can use it to do placement and other things, right? So simply because TSP and its landing pad is so big, you want to place them first and treat them as pre-placed, obstacles. Then with the space remaining, you can do placement routing. That's how I would approach it.
Do we have any question?
Very simple question. So in your placement, you can calculate the X, Y, Z together simultaneously rather than X, Y first and then Z.
Mm-hmm.
I think Z is discrete, which means not differentiable. I'm not sure how to solve it. It's a very simple question.
That's an excellent question too. So let's go back to my true 3D placer. So in our case, Z is not binary here, but then we treat them as a probability. So we use sigmoid function to limit, right, this guy to 0 to 1, floating point number. And then any number that's close to 0 will go to tier 0, and right. And then if your Z is 0.5, then you get confused, right? So turned out our loss function, because they try to minimize congestion and cut size and overlaps, they naturally, make Z close to 0 or close to 1 if you successfully minimize all this loss function. So in reality, if you look at optimized Z, it's very rare that I see 0.5. It's either very close to 0 or 1.
We have some questions received from online.
Okay.
Actually, we have received more than approximately 70,000 likes online.
What?
So many people, they are watching online.
How many?
More than 70,000.
Are you serious?
The number showed more than 70,000 likes. Yeah.
Wow, it's such an honor. Thanks so much. I've never seen this kind of big crowd before.
So the question is regarding module folding will have better PPA, but folding twice is still based on 2 dies instead of 2 to the power of 2 dies.
I wish I had that slide. I already showed you, right, during our meeting, with Huawei this morning. So I have done a work where I folded my design into 3 tiers, and I published a paper. So if you contact me, I can share that paper with you guys. So I compared 2D IC and 3D IC with 2-tier, and then 3D IC with 3-tier. Right? In my 3D IC with 3 tiers, some modules are folded into 3-tier, some modules are folded into 2-tier, and some modules are not folded at all. So I had to pack these different modules with different heights. In any case, 3-tier design had the lowest power, the best quality out of these 3. So the more tiers you have in your design, the better the PPA becomes. But to go from 1-tier to 2-tier, I had 20% power saving. But then go from 2-tier to 3-tier, right? I had like 7 to 8% power saving. So power saving, there's a diminishing return over here. So if you go to 4-tier, unless your EDA tool is very sophisticated, you may not get too much. So at this point, my thinking is 2-tier folding is a sweet spot, but that doesn't mean you will never get any benefit with 4-tier folding, right? It's just that your EDA tool may have to improve further. Right? But then more than 2-tier, if that's available, you don't need to use it for folding. You can tier more memory. Where you have 2 tiers used for folding and 2 more tiers to stack more memory. Then you can increase the memory capacity, right? So if you have more tiers, there's more things you can do with it.
Thanks. And actually, I have one question regarding the page 43.
43.
Yeah. So I was 42.
42.
Yeah. I was astonished by the number that showed more than 700 terabytes per second. Is this design a stack? Do we stack multiple SRAM on top of a compute die?
No, only 2-tier. SRAM on the top and logic core on the bottom. The reason why this is so high is because if you have 7 nanometer, right? First of all, from 130 down to 7, this is how many Moore's law jump? Many generations. So instead of fitting 64 core, I was able to increase number of cores like crazy. So each core fetches 32-bit. If you multiply this with 32, you get that, right? And then the way I arrive at this number, right, is this terabytes per second, right? So then what I did was 4 times, this many bits divided by 8, then I would arrive at the number. So, yeah, this is just math. I mean, I didn't fabricate this, right? but I mean, all this math, unless there's any mistake, I think it will tell me, okay, that data bandwidth.
So I guess Jason Huang from NVIDIA would be very interested in this kind of design. Because,
I want to show him this, right, if I do have a chance.
yeah.
Yes, sir.
However, during the runtime, some memory can be can be written. So that means if a memory write first, and then you need to wait several cycles to get it back, right? So there would be some trade-off.
That's an excellent point, right? So it also depends on the latency caused by the memory module itself. Yes, maybe memory read, depending on which address you go to, may take 2 cycles or 3 cycles until you get the data, right? But our SRAM used as a sketchpad memory, fortunately, it was 1 cycle operable. But then if you go to real commercial version of the architecture, you will never use this, to execute your AI workloads. So again, this is not apple to apple, but I still believe that if you do memory and logic stacking for your next version NVIDIA, Jensen, listen. Yes, thank you.
So do we have any question? Oh. Last question?
Yeah, sure, of course.
Yeah.
I'll be happy to.
Hello, Professor Lim. Thank you for your impressive talk. And I want to ask you some question about the power delivery network design for the face-to-face 3D IC. So I'd like to know how your Pin3D implement the power delivery network and how the power delivered to the chip. And how we provide the power for the cell in the top tier and the cell in the bottom tiers. Thank you.
Is there a whiteboard I can use here in this room? Oh, good, okay. So, that's the top die. And this is bottom die. This is face, and that's back. And this is face, and that's back. We assume that the C4s are on the bottom. So this is I/O, and this is power, and that's ground, and maybe that's another I/O, right? Then the way we deliver power is, first of all, you need a TSV that aligns with the power, right? And then power will be delivered, current will be delivered, that. And then your transistor in the bottom tier, right, will connect to this power source, right? And in the top tier, you're going to have, first of all, you need a via totem. Stack the vias, go up here, and then you will have face-to-face power pad, and you will have another totem, then you will connect the top transistor. So this is vertical power delivery path. So in Pin3D, what happens, right, is before, so if your design has memory macros and, gates, right, then before you do placement, I will place my memory macros first. The memory macros in the top tier, some memory macros in the bottom tier, I make them obstacles. Then based on this memory macros, I would lay out my power delivery network. I will decide, okay, M2 gets, 20% of M2 tracks, I will use it for power delivery. And 50% of my M6 track, I will use it for power delivery. Based on that, you write the script to do SRoute. It routes PDN wires, right, for the bottom and the top, right? So macro placement first, PDN routing next, cell placement next, clock routing next, signal routing next, IR drop analysis next, go back and fix my PDN based on IR drop map, repeat.
Yeah, really thanks for Professor Lim's distinguished talks. And that's all for our today's seminar. So finally, please allow us to give a big applause to our Professor Lim again. Thanks.
Thanks so much, appreciate it.
So we may take a photo together, and please allow our audience can come together and stand and come to the front side. And we use this as a background. Yeah. No.